Welcome to our lesson on resonance circuits. This is a key concept in understanding how devices like radios and TVs tune into specific channels, a technology we use every day in Nigeria. By the end of this lesson, you will be able to perform all of these objectives. Resonance in an RLC circuit is a special condition where the opposition from the inductor, called inductive reactance, XL, perfectly cancels out the opposition from the capacitor, called capacitive reactance, XC. First, let's quickly review these two types of reactance. Inductive reactance, XL, increases as the frequency F of the AC signal increases. It is measured in ohms. Capacitive reactance, XC, does the opposite. It decreases as the frequency F increases. It is also measured in ohms. If we plot both reactances against frequency, you can see that XL increases linearly while XC decreases. The point where they cross is the resonant frequency, FR, where XL equals XC. Now let's look at the two main types of resonance circuits, starting with the series resonance circuit. In a series circuit, the components are connected end to end. At resonance, a unique condition occurs. We can derive the formula for the resonant frequency by setting the reactances equal and solving for F. This formula is very important. At series resonance, the circuit has minimum impedance, allowing maximum current to flow. It behaves like a pure resistor. Let's solve an example. Consider a series RLC circuit with these values. First, we'll find the resonant frequency. We substitute the values for L and C into our formula. Calculating this gives us a resonant frequency of approximately 1.59 kilohertz. Next, to find the current at resonance, we use Ohm's law. Since impedance Z equals resistance R at resonance, the calculation is simple. The current at resonance is 2 amperes, which is the maximum current this circuit will allow. Next, let's examine the parallel resonance circuit, also known as a tank circuit or anti-resonance circuit. In an ideal parallel circuit, the inductor and capacitor are parallel to the source. Its behavior at resonance is the opposite of a series circuit. For an ideal parallel circuit, the formula for resonant frequency is the same as for a series circuit. At parallel resonance, the circuit has maximum impedance. This means it draws minimum current from the source. It acts like an open circuit for the resonant frequency. Let's solve a quick example for a parallel circuit. We have an inductor and capacitor in parallel. Let's find their resonant frequency. Again, we substitute the values into the formula. The calculation gives a resonant frequency of about 5.03 kilohertz. Two final important concepts are the Q factor and bandwidth. The Q factor, or quality factor, tells us how selective or sharp the resonance is. A high Q factor means a very narrow bandwidth, which is excellent for tuning circuits, as it can select a specific frequency while rejecting others nearby. So, how does this apply in Nigeria? When you tune your radio to your favorite station, you are adjusting the capacitance or inductance in a resonant circuit inside the radio. This changes the resonant frequency to match the station's broadcast frequency, allowing maximum signal to be received while filtering out all other stations. This is resonance in action. Let's summarize. Resonance is when inductive and capacitive reactances cancel out. Series circuits allow the resonant frequency to pass, while parallel circuits block it. Both are crucial for electronic communication.